Okay, hello. Today I thought I would do a quick video on optics, so I'll try to talk really fast. So if you want to hear anything, you might need to slow it down. That's an option. So first of all, waves. Basically, waves are governed by the cosine, usually cosine functions and sine functions, depending on the application. This is basic harmonic motion. We know that. And the properties of waves from this graph, we know that this, the height above the middle state, like the rest state, or the axis in this case, since I haven't added a constant here, is the amplitude. When it repeats, basically how many degrees go by before it repeats is always 2 pi radians. That's a full cycle. And the distance that occupies, which is basically from one point to where that point happened earlier, this, as I've illustrated here in a larger drawing, is the wavelength, which is mainly what we'll be discussing today. The wavelength is denoted in optics as a lambda, the lowercase lambda from Greek, and it is proportional to the velocity of this wave by the frequency, or basically 1 over the period of the wave. Now the frequency of the period, is equal to the cycles per second. I'm just going to denote with an S. And the period is equal to 1 over the frequency, which is equal to seconds per cycle. And that all makes sense. The words work. For once, physicists said, yeah, well, never mind. For once it makes sense. Although, yeah, why they couldn't call it time period instead, never mind. Now then, this equation here is very useful, and it's the kind of question you'll see on some a lot of basic optics tests, and it's going to be important later. And, just to prove this, if you want the notation, frequency being cycles per second, and this here, lambda, being the wavelength, or the distance, or in SI units, meters per cycle. How long is there between these 2 points for every cycle? So basically, distance per cycle, I'm going to write this, no, we don't want to erase this yet. So distance per cycle times, because we're going to see if it works out to velocity, cycles per second, those cancel out, distance per second, that's the same as velocity. Alright, so all the units work out. Good. We're going to leave this on the side, we're going to remember it, because it's very important to remember. I'm going to erase all of this, so that I can start anew. Now then, that is how you calculate basic values of a wave and how it's functioning. Now then, I'm going to introduce you to the Doppler effect, which you may have heard of, though this is an actual physical representation with equations. And a basic understanding is, let's say we have a source, S. Let's say we don't actually care about what the source is. We care about the velocity of the source. So the velocity of the source, let's say, is equal to, for now it can be a constant, but is equal to basically our velocity of the source, and then we have a velocity of the wave. And we could define these, but in this video, at least for right now, I won't, so that it's kind of vague. This may sometimes, if it's velocity of a wave of Sound, it will usually be 340 meters per second, or it really could be anything. So let's not even care about that equal sign for now. So we have the velocity of the source and the velocity of the wave. So let's think about what's happening if a source of waves, let's say light or sound or anything, is moving along while emitting these waves. So after 0 seconds, it's just sitting. We're going to denote it with a point. 1 second. At this point, it emits a wave right here. At 1 second, it's moved a little to the right or left, doesn't matter. And its wave has expanded. We're assuming that the wave's faster than it, unless this is sound in a supersonic jet. But that's a bit different. Though it's governed by the same equation. After 2 seconds, it's moved a little bit more, and the wave it emitted at that point has reached a certain radius, and this one has expanded even further. You may be noticing something. Then at 3 seconds, this has moved even further, and this cycle continues. They continue to be emitted and expand. And then this, of course, goes along forever. Okay, so now, how do we figure out the frequency for someone observing these? Or, let's say the period. That one's a little bit simpler. So the period for an observer on, how about the observer that it's moving towards? We're going to create an eyeball to be that observer. So the period between the waves, the time between the waves is, if we look at this with a different color, because this one's getting dull, this is going to be, so these waves, here, wait, what's this distance here, basically? That's what's important right now. So, so this little distance here. And we need to divide that, basically, by, this distance here needs to be divided by the velocity of the wave so that we know how much time it takes to get there. Now, this distance here is, let's imagine our dot in the center, because we're imagining that it's moving towards all the time. So, as it moves closer, this here is going to be basically, okay, let's look at the whole picture here. This whole distance, so the velocity of the wave times the time that's gone by, in this case the time of the source, minus this part right here to find this little part in between. The velocity of the source times the time. Now if we write this all out, and remember we're dividing this by the velocity of the wave, so is equal to the velocity of the wave, no, not the W, V wave, times the time that the source has been moving, minus the velocity of the source times the time that the source has been moving, divided by the velocity of the wave, which we can simplify to the time that's been moving times velocity of the wave minus velocity of the source over the velocity of the wave, and it's not really necessary to simplify any further. And of course this is equal to, I'm going to use blue again, the period between the waves. Now then, what if our observer was on the other side? Well, instead of subtracting these two, we'd actually be adding them. Because we want to find this distance here. So we have to add the velocity of the wave getting here, plus the velocity, here, the velocity of the source moving here, times the time, of course, so that we get distance for all of this to find this. From point 0, right? Because of the time that's gone by, right? So this is what we're paying attention to. And instead, let's say observer approach, and so then, hence, observer that it's retreating from would be the time that's gone by times velocity of the wave plus the velocity of the source over W, and we just we reverse this to find the frequency, right? So our frequency for, let's say, an object away would be equal to just 1 over time times the velocity of the wave over the velocity, ooh, I keep making W's. The velocity of the wave minus velocity of the source, and then if it was, don't want to write it again, but if retreating, it's a plus instead. It's a plus unless it's approaching, in which case it's a minus. It's just the sign's opposite. And that makes sense. Okay, so now what does this have to do with the wavelength? Well, if you were paying attention, you would know the velocity is equal to the wavelength times the frequency. And we find our frequency from here. It is changing, because imagine, this is changing constantly as time goes by. So our frequency is changing all the time, getting smaller, right? Because this is a constant, and you're just dividing by more and more. So our frequency of the waves, as it's, well, going away, coming towards, is actually getting smaller. Our period's getting bigger, of course, because it's the inverse. And let's just simplify. Our wavelength is the velocity divided by the frequency. And because the frequency is changing, our wavelength is also changing. So the Doppler effect applies to all of these different segments. The velocity were remaining constant, which is why this is that our wavelength most definitely changes with the frequency. That's a basic introduction to the Doppler effect and the equations that govern it. Come back next time.